Morning, guys. So yesterday we started introducing how we can plot on a graph a person's position as time ticks forwards. We were using the simulation here. We'll use it a little bit more in today's lesson here. Again, I want to emphasize to you the variables that we talked about so far, position, velocity, and acceleration. These are completely independent of each other. Your position tracks your whereabouts. So sure, if it goes to the forward direction here, we say to the right is actually positive. We have distances 2 meters, 4 meters. Going the other way here is actually negative. Distance-wise as a scalar, it's still a positive 2 meters worth of ground that's covered, but we just use that negative. We pop on that negative just to indicate to you the direction. So his position actually doesn't depend on what happens to velocity and acceleration. I can be in front of the line positive, I can be behind the line. Just because I'm in front of the line, let's say I'm in front of the line here, just because I'm in front of the line doesn't necessarily mean I have to necessarily be going forwards. We've done graphs from yesterday. Oh, I happen to be in front, but let's actually start off with the negative velocity. Let's show that velocity vector here. Vectors are arrows, so usually I imply here by the size of the arrow here by how much that velocity is going to be. So speed is totally irrelevant on where the guy is currently standing. I happen to be standing at a positive position, but his velocity is actually negative. And also independent from this here is actually acceleration. Sometimes people are tempted to say, oh, if I go backwards, oh, I have to be slowing down. Well, no, the backwards is just a heading. I can have an acceleration that's in the same direction. If I have in the same direction, after every second, you're going to be 4.63 even faster than you were to begin with. Whenever these two are the same sign, negative and negative, we're going to be speeding up. We can watch that happen there, right? It could also be sort of, my velocity is positive. You'll notice that I'm sort of way at the back here. My position is actually way negative, but I can still go forwards. If I'm going forwards, I can still have a negative acceleration just because they're totally independent here. Whenever these two sort of fight against each other, it's still going to take a little bit of time to gradually come to a stop. I'm actually traveling through some positive distance. It's gradually bringing you to a rest until the fact that you're actually at zero. When you actually change direction, now my velocity and acceleration are in the same direction again. Now it's good to start speeding up. Granted, the acceleration rate is actually fairly slow. That's why you're not going to be really track the increase in speed all that easily. What we did is we started looking at plotting, again, his position over the time interval. Today, we're just going to recap a position time graph and try to transition over to something called a velocity time graph instead. So again, let's just toggle over to the charts option here. For the charts option, what we have here is we have, again, our guy can go forwards, can go backwards, positive and negative. We have a position time graph, which we talked about a lot in yesterday's lesson. We're going to focus mainly on a velocity time plot for today. And again, I'm not going to worry too much about an acceleration time graph for now. So we know a little bit of familiarity here with this sort of the top of the graph here. Let's just do a motion here. What I want to show you here is they've actually done it really cleverly here. Time is a scalar. Time doesn't care whether you're trying to plot it on a position time graph or a velocity time graph. When it says 2 seconds on your position time graph, it still says 2 seconds on a velocity time graph. That's actually going to help us convert between one graph and the other graph in tomorrow's lesson. But for today, again, I just want to introduce to you some things we can calculate on this velocity time graph. So what I'm going to do is I'm going to do some sample motion here. I'm going to try to drag this guy here forwards at a constant velocity if I can. I'm going to get him to just stand there for a while. I'm going to get him to speed up going backwards and then maybe slow down. And let's do that one more time. Speed up and slow down, right? You can actually play around with a little bit more here. Again, this is plotting in real time. That's why depending on sort of how steady I was in holding the guy here, you can actually see the cursor actually changing. But let's see if we can analyze sort of parts of this motion. What I just want to introduce to you here, we already have some familiarity with position time graph. Let's see if we can read this. Well, as the graph goes into the top, I'm guaranteed he's going to be in front of the line. As time ticks onwards, he's getting more and more positive. So I know he's heading forwards. I was trying to drag the guy here forwards at a constant speed. We saw that speed or velocity was given by the slope on a position time graph here. The speed here is actually constant. This is actually going to look a little bit weird on a velocity time graph. Think velocity time graph here. I don't care where he is. All I'm plotting for you here is how fast he's going. So if I could have made this line here a little bit more steady, his constant slope, I would actually say, let's say his constant slope here was 1 meter per second, right? After every second he's 1 meter away. What would end up happening is at 2, he's traveling 1 meter per second. A little bit later, he's still at 2 meters per second. A little bit later, he's still at 2 meters per second. If I could have dragged this here much more steadily, instead of having these little minor blips here and there, I would have actually saw a steady line here. I don't really care where he is or how far he gets. I just know that over the course of this time interval, the slope is not changing. His slope is just, his speed is not changing. So this one here should have been a nice steady line, nice and horizontal. What about over here? We know that at this time here, he's at about 4.8 meters. A little bit later, he's still 4.8. A little bit later, he's still 4.8. We saw that, well, the slope is 0. We know that his speed is 0. He's actually come to a stop. For speed being 0, because this is actually plotting the speed on the y-axis, speed equals 0 is exactly on the x-axis. Not only is this one here going to be constant and unchanging, it's actually going to be constant at 0. At 6 seconds, it's 0. A little bit later, it's 0. A little bit later, it's 0, right? So that doesn't change. Then what I do was I pulled the guy backwards. I tried to have at first a really sort of fast speed and then slowing down. What's happening here is we're going from that rest to travel at a negative velocity, means this graph here actually has to drop below. As I drop below here, again, we can read the velocities just directly on the y-axis here. At first we were 0, a little bit later I was at -1 meter per second, a little bit later I was at -2 meters per second. I'm just matching it up against the y-axis. We see that the speed is actually changing. I'm going -1, -2, -3 or so. The negative just tells me it's backwards. It guarantees I'm getting closer and closer to the starting line. But because the magnitude is getting bigger, I'm going from a speed of 1 to 2 to 3. That actually implies I'm speeding up. I end up hitting a max speed of about, let's say, -8, -9 or so. And then what I do here is I gradually bring him to a stop, right? The slope gradually sort of lessens off here. And as it lessens off, we see that the speed actually starts decreasing again. The speed actually starts coming back upwards. We start going from -8, -6, -5, -4, -3. Again, the negative still tells me, yes, I'm still traveling backwards. But because, again, the magnitude is actually dropping, the speed is actually steadily decreasing. We have another segment that I just left him there, and then I start pulling him downwards again. Anytime this slope is negative, because this slope is the velocity, I would expect the slope to be in the negative region. Anytime we're below on this graph here, it actually means backwards. So in this lesson, I just wanted to introduce to you how do we make interpretations reading on velocity time graphs, sort of the advantages of doing a velocity time graph, and also because a velocity time graph doesn't actually care where he is. I could have started out way in front and did this motion. I could have been way behind and did this motion here, but I'm just tracking for you his speed over the course of the motion. Again, with the advantage, I'm not just doing start and finish, initial and final, blindfolded, but I'm actually seeing what is his speed as time ticks forwards. Right? So with that, let's switch over to our OneNote and let's see how we do. Okay, so just like we did on our simulation here, what we want to study today is something called a velocity time graph. Although you may have seen a position time graph in earlier science lessons here, typically I find this is new to people. For a velocity time graph here, as the name suggests, this is going to describe the velocity of the person at any given time. It's not just start and finish, right? Our kinematic equations gave us that information really well. But what if I was interested in sort of tracking what happens over the course of the motion? I'm not actually blindfolded. So, as the name suggests here, we're going to plot velocity against time. Velocity is the y-axis and time is the x-axis. We'll come back in tomorrow's lesson to talk about how do we convert from one to the other. Today is just trying to read this graph here. So let's just put some numbers to this here. My velocity is 0. When your velocity is 0, it means that we're actually stopped, we're actually at rest. So any time that this graph here intersects with 0, we know that you've actually come to a stop. Now, because time can keep ticking forwards, I can stop at 0 for a long period of time. If it's like I throw an object upwards, I might hit 0, but I only hit it for an instant of time. Later, the velocity changes. But nonetheless, if it crosses this axis, we know it's 0. All we can guarantee is if we are above, it guarantees that the velocity is positive. Maybe +1, +2. What does it mean for velocity to be positive? If velocity is positive, it means actually the direction is forwards. Right? I'm actually heading farther and farther, right? However, remember, position is something totally separate. I may be starting way behind the starting line. Just because I'm behind the starting line doesn't necessarily mean I actually have to be traveling backwards. I'm just standing behind the starting line. As long as the graph is above the axis in this case here, it means my heading is forwards. It means if I was way behind, it means I'm going to get closer and closer to the starting line. If I was already at the starting line, I just keep getting farther and farther in the positive direction, in the rightward direction, in the upwards direction. As long as the graph is above, I know I'm going forwards. That's going to save your interpretation a little bit. What happens as the velocity drops into the negatives? If the graph actually drops into this lower region, so -1, -2, -3 as an example. Well, when velocity drops to negative, we had said negative velocity actually means backwards. Again, regardless of where I'm actually standing, I might be in front, I might be at the flag, I might be behind. As long as this graph here it drops below, it actually means I'm heading backwards from where I'm currently standing. One thing here that's sort of implicit here is I have no idea where the guy is. All I'm doing on this graph here is I'm trying to plot for you what is his speed over the course of the next time interval. All right. So let's just sketch out a few shapes here and let's see how we do with our interpretation. First part, let's do a line that goes up like this. Okay, let's say that's segment A, and then a line that does this, segment B. You might remember this shape here from yesterday. It's possible, just like we saw in our simulation, that we could actually have curves, but because in Physics 11 and Physics 12, we're always under the impression that acceleration is actually a constant, what we're going to have is we're actually going to have no curves on this graph here. So let me just make that note here. Although it's possible, for us, we're going to have no curves on a VT graph, and we're going to see this is because we're going to always do constant acceleration. And we'll talk more about that in a second here. All right, so we have it going upwards, we have it doing this. Because this one here is not plotting position, it's not plotting your whereabouts, this graph here can jump around a bit. So what I want to do here is, from doing that, I want to actually jump down over here. Right? If I actually did this on the graph here, sure, you would have a very steep, very sudden sort of fall like that. But unlike sort of, if this is position, like sort of you ran back at like an instantaneous speed, this is just tracking your speed, right? I switched from having a positive speed to a negative speed here very, very quickly, right? That's possible. So this graph here can jump around a little bit here. And let's do one more part motion. Let's again jump down again here. Let's jump down to here. So let's see if we can make an interpretation in this graph here. What is this guy doing in each of these segments here? Again, try it out for yourself, right? We'll put some numbers and calculations to this very shortly. But see if you can make a list for yourself here in segment A, B, C, and D. When I say describe the motion, usually what I'm interested in is tell me something about his direction. Tell me, is the velocity positive? Is it negative? Is he heading forwards, backwards? What's he doing? And tell me something about the velocity. Is it constant? Is it changing? Is it speeding up? Is it slowing down? What's happening? So again, I encourage you just to pause the video and give it a try for yourself. Right? All right, let's take a look at part A here. Again, what's constant in this case here is time. Time just keeps ticking forwards regardless of where he is, regardless in this diagram of what he's doing. But what I know here is at first, at 0 seconds, I happen to have a speed of 0. A little bit later, I have a speed of, 0.4. A little bit later, I have a speed of 1. A little bit later, I have a speed of 1.5. Notice that I'm in the positive region, so I know right away my direction should be forwards, right? Because my velocity is in the top region. I'm heading to the right, I'm heading upwards. So this one here is forwards, because that's given by the positive velocity. But in terms of the speed, is it constant or is it changing? Well, definitely it's changing, because I was at 0.5, now I'm at 1, now I'm at 1.5. And in fact, this number here is steadily getting bigger. I can even comment here, this is actually speeding up. Again, that's usually a temptation. Oh, if I'm going forwards, I have to be speeding up. Well, no. Direction and velocity are something totally separate. I can be heading forwards, but I can actually be slowing down. So keep these two concepts as separate as you can. Earlier, when we did a displacement time graph here, when we had a level line like that, we would say, oh, perfect, we're not moving anymore. Is that true? On a velocity time graph now, at this time, I'm traveling at 2 meters per second. A little bit later, I'm still 2. A little bit later, I'm still 2. A little bit later, I'm still 2. Well, my velocity is 2. It's not 0, right? 0 would mean rest. So in this case here, my velocity is actually positive 2. Over the course of this time interval, it's positive, so I can still guarantee we're going forwards. It's positive. But in this case here, I actually have a constant velocity. I'll even make a note to you. It's a constant velocity of 2 meters per second. How did I get that? I just read the y-axis, right? The y-axis plots me the speed. At this instant, I'm at 2. A little bit later, I'm still at 2. A little bit later, I'm still at 2. it's still constant, it's unchanging, but my position is actually changing. I am traveling at a constant speed of 2. Now we have a weird part here. This one here just sort of skips downwards. As it skips downwards, it now enters into the negative region. As it goes into that negative region here, now I'm entering into the negative velocities. Now it does actually mean backwards, right? Backwards because I am lower than the x-axis. In this case, however, my speed, I go from a speed of having -2, a little bit later I'm at -1, a little bit later I'm at -0.5 or so. I'm just sort of matching up to the y-axis here. As time just keeps ticking forwards, my speed is going, again, mathematically I'm going -2 to -1 to -0.5, something like that. Yes, I'm getting closer and closer to 0 on the starting line. The negative, just like we said yesterday, the negative just tells you backwards. We already knew that, backwards. What I care is the size of the number. My size is going from 2 to 1 to 0.5. I'm not getting that much ground, so therefore I actually have a slowing down. Right? So in that case, I'm at constant 2 for a little while here, and suddenly I decide to switch directions. I travel really, really quickly backwards, but I gradually get slower and slower and slower. If I actually intersect here, I have a potential of changing direction. I could have switched from backwards into forwards, but nope. This one here decided in segment D, we still decided to come back down this way, and now my velocity is still in this bottom region here. I still know it's backwards. Again, the temptation is, oh, if it's backwards, it must be slowing down. Well, no, in this case here, it is backwards because my speed is -3. But you notice at this time it's -3, a little bit later it's -3, a little bit later it's -3. My speed isn't changing. It's a constant backward velocity of -3. So constant, remember, it just means unchanging, but it doesn't necessarily have to mean 0. Right? So you see that this graph here is slightly harder to read here. We'll do some more practice with the next graph as well. I just want to introduce to you sort of the 2 main things I can calculate from this graph. First one here is this comment here. Well, we have been assuming that acceleration is constant. Why does that mean that there can't be any curves? Let's look back at our kinematic formulas. If I look at the definition for acceleration, acceleration is actually given by change in velocity over change in time. Graphically speaking, if I wanted to find a change in velocity, velocity is on the y-axis. Let's look at segment B, because let's look at segment A here. The change in velocity is given by the rise again. It's given by how far up and down this one is. So this one here is the rise. Again, this is a velocity versus time. So going across here, this is actually an interval of time. What if I do a rise divided by run? We did this before. Oh, this is just a slope. Now, yesterday, the slope on a position time graph meant velocity. In this case here, the slope, I'm going to emphasize here for a VT graph, for a velocity time graph as we're looking at right now, the slope of this velocity time graph is actually the acceleration. So the reason why, if we assume that acceleration is constant, not that I don't have acceleration, but if we assume whatever acceleration I give you, whether positive or negative, if that number doesn't change, that means the slant of this line can't change. Because what's going to happen here is, although there is an acceleration, although your speed will change, the rate at which the speed changes has to be constant. So if it takes me, let's say, 1 second of time to speed up by 1 meter per second, it needs to take me that same 1 second of time to speed up to 2 meters per second. The slant can't change because the slant is actually given by the acceleration. So we're going to always have constant slopes, so no curves to worry about in this case, but be really careful, especially on tomorrow's lesson, when we start saying, okay, your acceleration is constant, your speed is sort of increasing by the same amount in each second, but remember for position-wise here, depending on your actual starting speed here, you might actually start covering more and more distance, right? So that you still might end up with a curve on a position time graph. It's just on a velocity time graph that is actually constant. So the slope on a velocity time graph is given by acceleration. If you want to practice that here, we had mentioned here, in part A, we're actually speeding up. Well, if I want to find the acceleration at that point, I want to pick any 2 points that are easy to read on this graph here. I noticed that I didn't actually give you a time interval. Let's say it's 5. Right? It could have been anything. You just read it from your graph here. All you would do is you take your coordinates. Well, this coordinate, that's easy to read here. This coordinate here is the coordinate 5, 2, right? X-axis 5, y-axis 2. This coordinate here is 0, 0. I can do a slope by doing y2 minus y1, x2 minus x1. I'm going to put in y2 as my 2, 2 minus my 0, divided by 5 minus 0. oh, therefore my acceleration is a constant 0.4 over that entire interval. Your speed is actually changing by 0.4 for every second that you travel, right? And again, I just want to verify this for you here. You'll notice when my direction is positive, right, I'm going forwards, and my acceleration is positive, that's sort of like velocity is heading one way, acceleration is going one way. That should mean speed up, which is exactly what we had calculated there. Let's test part C here. I'm not going to do it sort of with the math, but let's just test the sign. So part C, I'm into the negative velocities. I'm into going backwards. So this is negative. And yet this is slowing down. I would imagine that this car is trying to go backwards. I better have an acceleration that's positive, right? Because the only way for me to slow down is for these to be opposites. Because acceleration is a slant, acceleration is a slope given by this. When the slant here, remember the slant starts from 0 like this. When the slant here starts getting steeper and steeper in this orientation, this slope here is actually positive. So perfect. When I'm heading backwards, negative velocity, if I have a positive acceleration, those are opposite of each other, so therefore it actually slows down. If you actually want to find the size of the acceleration, you just go rise over run. That's definitely something I'm going to be asking you in the next problem. The one other variable that I can be asking for is displacement. So far we've been doing this and we've been saying, well, I have no clue where he is. Is he in front? Is he behind? Is he going forward? Is he going backward? Like, I can only track his speed over this time interval. If there was a way for me to actually find the displacement, that would be helpful. And in this case here, looking at segment B is actually really helpful. In segment B, he travels at 2 meters per second, and he travels at that between 5 seconds and 10 seconds. So for 5 seconds of time, he travels at 2 meters per second. Can you calculate the displacement? Well, sure. For every second that he travels, he gets 2. If he does that for 5, 2 times 5 gives you 10. What we're actually doing is we're actually using the displacement formula, actually a basic motion equation. D is equal to speed times time. Anytime you're interested to find the displacement, is sort of how far he gets, all you need to do is calculate what is his speed, what's his velocity, and multiply it by how long does he do that motion for. Well, that's nice. In this graph here, my speed is given by the y-axis. That's sort of this delta y. My speed was 2. And I'm multiplying by time. Well, that's nice because time is the x-axis. Geometrically, what I've actually found here is actually the area under the curve. So because of that formula, we see that really well in this segment here. Even when the speed is changing, when it looks a little bit harder, if you can somehow find for me the area under the curve, the area that's bounded by the curve, it actually will tell me the displacement. Again, something intrinsic is I have no idea his starting position, but if I can calculate the area, if I can do this velocity times time, this velocity times time just amounts to actually the area. Usually we do say the area under the curve. Just be careful here. That works really nicely for positive regions when the curve is up high like this. Well, yeah, this is the area under the curve. What if the curve drops down like this? I'm not talking the area under the curve. I'm not always saying, oh, it has to be below. What I'm actually saying here is the area that's bounded by the curve. The area between your curve and the x-axis. Right? And in that case there, when your areas drop to the negatives, negative means backwards. Even though I can calculate the area as a positive number, this negative means I actually lose this ground. I actually lose more ground there because that one there is also negative. So at least for a velocity time graph here, there's two things you can read. The slope gives you the acceleration. The area under the curve is the displacement. Now you might start thinking here, how come we didn't do area under the curve for a position time graph? It doesn't give you anything of significance. It was only in this graph where that actually became significant. So let's work through a problem together here. Let's put numbers to this. So here's our velocity and our time graph. Let's go up, let's say 5, 10, 15. Those are positive velocities. -5, -10, -15. Sure, let's go up in 2s again for time. You'd usually be given this graph and you're just asked to do an interpretation. Let's draw a few segments here. Let's start off with a segment that starts off like this. So between 0 and 2, that's the axis. Then it does this. Remember, no curves on a velocity time graph because the acceleration has to be constant. This one can skip around, so let's say it skips to this. And then it does this. and then let's do this. Okay. So first style of question here is just interpreting through, can you tell me what's happening to this object in each of these time intervals? I don't need to say A, B, C, D because I actually have the time readings. So they might say, can you tell me something about the direction? Am I heading forwards, backwards? Can you tell me something about the speed at each of these time intervals? So between 0 and 2 seconds, 2 and 4, 4 and 6, 6 and 8, and 8 and 10. All right. So again, I'd encourage you just pause the video, see how you do. Use that hint for yourself here. For a velocity time graph, as long as the graph is up here, it has to mean forwards. So right away, my graph is up here in first segment, second segment, and last segment here. I know right away this is forward, and this is forward, because I'm above the graph. Now the part that may have confused you here is, wait a second, this one here is actually starting to drop. Doesn't it mean like backwards? Doesn't it mean like, okay, we'll talk about that. But as long as your speed is actually a positive number, positive 10, positive 9, positive 8, positive 7, positive 5, positive whatever, it's positive, it's still forwards. So those are forwards because the velocities are positive. So positive velocity, positive velocity. Whenever the graph drops below the graph, drops below the axis here, it means your velocity starts switching over into the negatives. So as long as we're down here, it means we're actually going backwards. Notice again, what it doesn't say is, it doesn't say we're necessarily behind the line. We could be really, really far in front of the line, but it's just over that time interval. We're going to steadily start heading backwards. So as I head backwards here, we have some negative velocities. So this one here is backwards, BKW, BKW. This is negative velocities like that. We switch from going backwards to forwards. So that's where it happens. That's where I potentially switch direction. That's when your velocity is 0. That's the only time we can cross over from going backwards to forward. So we actually switch direction. We switch over from negative to positive. Probably more interesting for us here is actually the speed. What's happening? Is it constant? Is it changing? Is it slowing down, speeding up? Let's try it. So between 0 and 2 seconds, at 0 seconds, you're traveling 10. A little bit later, you're still 10. A little bit later, you're still 10. What can you tell me about the speed? Well, we actually have a constant speed, our constant velocity of 10 meters per second. Well, actually, that tells me about acceleration. Maybe I'll actually even leave you a column for acceleration there. For acceleration, we actually have, well, acceleration is given by the slant of the line. Because the slant here is actually 0, the acceleration is actually 0 meters per second squared. So that's why we can actually stay at a constant 10. That number doesn't need to change. Now let's come back to, well, I thought this was actually walking backwards. Well, no, we're walking forwards because the velocity is positive. The thing that's turned negative is actually the slant that is actually turned negative. As the slant turns negative, we actually have a negative acceleration. What if I'm trying to go forwards and I have a negative acceleration? When those oppose each other, that has to mean a slowing down. We can read that from the graph here. Well, at 2 seconds, I was going 10. A little bit later, I'm only going 8. A little bit later, I'm going 6. A little bit later, I'm going 4. My number is getting smaller and smaller. It's still positive, still going forwards, but the magnitude is getting smaller, so I'm actually slowing down. This part here, again, back to having a constant slope here. If acceleration is 0 meters per second squared, sure, we happen to be going backwards now, but in this case here, it's actually a constant velocity. That's a constant velocity at negative 10, so be it. Can you interpret this part for me? Right. So at 6 seconds, you're going at negative 10, a little bit later, negative 8, a little bit later, negative 6 here. Again, looking at the numbers here, I'm sort of ignoring the negative. I already know negative means backwards. What I'm interested in is the size of the number. If you go at a speed of 10, then 8, then 6, because the magnitude itself is getting smaller, it equally well means slow down. For me to slow down, if my velocity is negative, my acceleration has to be opposite. My acceleration would actually have to be positive. Is that true? Well, yeah, a slant that goes this way is actually a positive velocity here. And now lastly, by the time you actually switch direction, by the time you actually come to a stop, you come to a rest, now that we're switching back into the positive velocities, what does it mean if you're going positive velocity and the acceleration, the slant, sure, it's not as severe as the one before it, but the acceleration is also in the same direction. This one has to imply here speed up. And there we go. We go from a speed of, at 8 seconds, we're at 0 meters per second. A little bit later, we're at 1. A little bit later, we're at 2. A little bit later, we're at 3. And the advantage of doing a velocity time graph is you can just look at the y-axis, and that actually directly gives you the speed there, right? So that's sort of one style of question. just given a graph here, see if you can interpret these numbers here. I'm going to ask you sort of those two calculations here. One is, can you calculate, so we've sort of predicted the signs of the acceleration. Can you calculate the acceleration at 3 seconds? That sort of sounds like an instantaneous acceleration. That sort of sounds like I'm only interested in exactly when the clock says 3. Again, we have that problem, oh, I can't find the slope of a single point. But what you're going to find is, because we said there's not going to be any curves, we're going to find you can draw your tangent line. Basically, your tangent line will basically follow the straight line. Choose any 2 points that are easy to read. So for example, this point on top is easy to read. That's at 2, 10. This point here at the bottom is easy to read here. That's at 4, 0. We know the acceleration is given by the slope of this graph here. Slope is given by y2 minus y1 divided by x2 minus x1. And here we go. 0 minus 10 divided by 4 minus 2. And that gives you here negative 10 on top to your acceleration is negative 2.5 meters per second squared. We had already said that it was negative, so consistent, perfect. So we won't have to worry about tangents in this case here because we slightly sort of simplify it. We don't have any curves on this graph. What's more interesting, however, is I might ask you, I want to know what is calculate or find. Calculate the displacement between, let's say, 0 and 8 seconds. I don't have to do the whole time interval. I just want 0 and 8. For you just need a track here. Well, for displacement, I need the area under the curve. What I'm going to do is I'm going to do a little bit of geometry. I need to find this area, right? That area would have a length of 2 multiplied by 10. So what I'm going to do here, the displacement is a bunch of these areas. That first box, right, length times width. Length is 2, the up and down is 10. That first area, 2 times 10, oh, I actually went positive 20. In the next area here, oh no, this part here is actually a triangle. As it becomes a triangle, we go base times height divided by 2. The base is 2, the height is still half. So we're going to go 1/2 base times height. Right? So I'm only going to get 10 in that interval. Uh-oh, now your area switch over into the negatives. You can still calculate your area pretty easily. I can go, well, this interval here is now a negative 10. I'm actually going backwards at 10. I do that for 2 seconds. So what I'm going to add is I'm going to do a negative 10 for 2 seconds. That's going to get rid of 20 meters. And then again, we have a triangle. This triangle here is perfectly symmetrical with the other one. So we have, again, a negative 10. That's how far it is. And then we have this side here is just 2 seconds worth of time. Negative 10 times 2, base times height divided by 2. The height was a negative 10. My first interval should have taken me 20 meters. Then the next one takes me 10. Then the next one gets rid of 20. Then the next one gets rid of 10. Oh, overall my displacement is actually 0. So, did I actually move? Yes, I did. I moved forwards, I slowed down, I started moving backwards, I slowed down again. It's just over the 8 seconds, wherever you were starting, these areas ended up canceling out. So positive areas up here, negative areas down below. So pretty much if you can find the areas, you can find the displacement for that time interval. Now the one other just caution I have for you here is when you try to calculate this area, sometimes you may get this graph here. Sometimes as you're trying to find an area, let's say it's 0, let's say it's 5, and 10, velocity versus time, sometimes you might get a shape like this, right? So all I said is you just have to have straight lines. It doesn't necessarily mean that there's a curve. That's still doable. I still want to get the area under the curve to find, to try to find the displacement. In this case here, you might recognize it as actually a trapezoid. There is actually a formula for a trapezoid, right? But I usually don't memorize that. I usually would separate. I need the total area to get the displacement. I just break up this trapezoid here into a triangle and a square. I know how to do the area of a square. This part here is going to be base times height. I know how to do the area of a triangle. This is going to be 1/2 base times height. And I just add those two areas, and that would give me the total displacement that I travel within that time interval. So keep practicing through your worksheets there, and we'll go from there. Thanks, guys.